Hey, grade 8, a bit of a shorter lesson today. We're going to talk about the particle theory of matter and kind of talk about the points of it and how when we look at matter and the different states, how it's all made out of particles. This is in the theoretical, right? So yesterday we were dealing mostly in the empirical, talking about filling up the volume of a container or taking the shape of a container. And now what we're talking about is actually theoretically, what are the particles doing? So when we look at the little bits of matter, right? The molecules that make things up. What are those molecules doing? So here's the particle theory of matter. A few points. Number one, all substances are made up of tiny particles. If I take any matter at all, right, and then I keep on breaking it up into smaller and smaller and smaller and smaller pieces, eventually I get to the smallest piece that is still that substance that the matter is made out of, if it's a pure substance. So for example, if I have an element, then if I keep on going down smaller, I'll get to an atom. And if I have a compound, I keep on getting smaller, I'll get down to like a molecule. You're going to actually, we'll talk about that more when we get to classification of matter, but what you need to know right now is that we have these little tiny particles that make things up. So for example, if I take a look at water, right, when I look at the tiny, tiny particles, it's made up of H2O. So I have two H's connected to an oxygen, two hydrogen atoms bonded to an oxygen atom, and that's what water is made out of, is a bunch of these H2O particles. Kind of an interesting fact is that an ordinary snowflake, right, incredibly tiny, but that has 1,000,000,000,000,000,000,000,000,000,000,000 particles in it. In other words, 10 million particles in there. A way that sometimes we show this in science so that it is easier to represent the number is we go ahead and count the zeros. So I have 3, 6, 9, 12, 15, 18, 19, and then I say 1.0 times 10 to the 19 particles. That's another way to represent it. That's called scientific notation. Anyways, all substances are made of tiny particles. Number two, the particles are always in motion. They're vibrating, they're rotating. If we have a liquid or a gas, and they're also moving from place to place in a gas and also a bit in a liquid, what we call translational motion, right? So we have all these different types of motion that are taking place within matter, but the type of motion that's taking place depends on the state that it is. Temperature, and you learn this in Science 7, is a measure of the average kinetic energy of particles. So when I measure temperature of something, I'm actually measuring how much stuff is moving. Okay, number three, all the particles in a substance are the same. Different substances are made of different particles. So when we take a look at any substance and we break it into the smallest particle, that it's still, if it's a pure substance, they're all going to be the same. So, I mean, we just went through the example of water where it's H2O. If I take a look at, for example, table salt, that's sodium chloride. So when I actually break it down further and further and further, eventually I get to the point where I have one sodium ion and one chloride ion, right? And that particle is what salt is made out of again and again and again. It's a bit of an oversimplification, but that's what's happening. If I take a look at, for example, what you're breathing out of your mouth right now, carbon dioxide. Well, every particle of carbon dioxide is CO2. It's a carbon that's bonded to two oxygen atoms. Okay, so all the particles are the same within pure carbon dioxide. Number four, the particles have spaces between them. Now, the amount of space will depend on the state that we have. So you learn that in solids and liquids, particles are really closely packed together. Well, in a gas, particles are very spread out and very far apart, which is why they can be compressed. It's because there's all that space between particles, so they can be compressed in order to lower that amount of space. But there's always spaces between particles, no matter what. We always have spaces. And in fact, even within atoms, we have large amounts of just empty space. Number five, there are attractive forces among particles. These can be strong or weak depending on the type of particle. This is something that I teach a ton of in Chemistry 20. We actually learn all about the different attractive forces between particles. And we even get so far as we're able to predict which one is going to have a higher melting point? So turning from a solid to a liquid, or a boiling point, liquid to a gas. And we do that based on figuring out what the attractive forces will be between particles. Water is another just great one to talk about here, because in water we again have that H2O, right? And water, for its size, it's a very small molecule, but it actually has quite a high melting point at that 100 degrees Celsius for water. And the reason why is because water molecules are incredibly attracted to each other. In fact, here's something you can do at home if you have a balloon. Okay, little experiment here for you to try out. If you have a balloon, blow it up, okay, rub it on your hair or your clothes to make it all staticky, and then run your tap, your kitchen faucet. And what you're going to do is take that staticky end of the balloon and put it towards the water. And what actually happens is the water is going to bend, the stream will bend towards the balloon. And the reason why that's happening is because water actually has a positive end and a negative end. It's got like a side that has more electrons and a side that has more protons. And so the side that has more, I think it's protons, attracts to the electron buildup that you have on the balloon. And we're getting into kind of like science you haven't learned yet, but yeah, it's just neat that we can actually see some of these attractive forces. Water has extremely high what we call cohesion, which is water sticks really well to other water. And that's why when you have like droplets of water on a table or something, you can actually see how it like kind of does this shape where it's like this, right? And that's because of the high cohesion that water has. Anyways, number 5, there are attractive forces among particles, and these can be strong or weak depending on the type of particle we have. So now, a few questions, or at least one here. How does the particle model of matter explain why solids cannot be fluids? So what about solids and what the particles are doing doesn't allow them to flow? Try answering that now in your notes, your fill-in-the-blank notes. See if you can come up with a good reason. Let's talk briefly about changes of state. This is something you talked quite a bit about in Science 7, so it's nice to tie in what we're learning here to things you already know. You know that solids, liquids, and gases can change state when energy is given to or taken away from particles. So solid is the lowest energy state. Think of ice, right? And then as I add energy, I add heat to it, then it will change state to become a liquid. And then a liquid, if I add energy to it, will become a gas eventually. So as I go from solid, liquid to gas, I am absorbing energy. I'm putting in energy. You'll learn in Science 9 that we call this an endothermic process, which means energy is going in. When I'm going down the state, so I'm going gas to liquid or liquid to solid, if I'm going down in energy by going to a lower energy state, then this is releasing energy. It's letting, whoa, something weird just happened there. It's letting energy out. Okay, now talking about this a bit, when you actually, let's say, make ice in your freezer, yes, the water is releasing energy as it's turning into ice. And what your fridge and freezer is doing is it's just pumping the energy out of the fridge, right? So if you go to the back of the fridge, you'll find it's really hot. That's where the energy is being released. It actually has to do with condensation and evaporation of the refrigerant that's in there. But the back is actually where the heat is being essentially pumped out. Oversimplification again, but you get the idea. So when water turns to ice, liquid water turns to ice, it's releasing energy during that time. Here are the changes of state. You learned all about this back in Science 7. You should know all these terms. So solid turning to a liquid, that's fusion. Liquid turning a solid, that's freezing, or solidification is the more technical term. Solid to gas is sublimation. Gas to solid is also called sublimation. Sometimes we call that deposition. Liquid to gas is evaporation, and gas to liquid is condensation. Okay, so let's talk a little bit about the specific examples and whether energy is going in or going out. So if I have a solid going to a liquid, okay, so I have melting or fusion happening, You tell me, is that absorbing or releasing energy? Okay, so if fusion is absorbing energy, then solidification is going to be releasing. I like to think of this as one of those doors that opens both ways, right? That you see in like a restaurant where it opens this way or it opens the other way. It's the same door though, right? So if I'm going through from solid to liquid and that's absorbing, then this is just the opposite direction. And so it's going to be the opposite process. And in fact, the amount of energy it takes to melt something is the same amount of energy that gets released if it freezes again. Okay, same thing here. I have liquid going to gas. So you tell me, liquid going to gas, let's do condensation this time. Gas going to liquid, is that going to release energy or absorb energy? So because going from gas to a liquid is going to a lower energy state, right? Liquids are lower in energy than a gas for the same substance. So because it's going to lower energy state, it has to release energy. So it's letting energy out in order to go to that lower energy state. That means evaporation is absorbing energy. And then sublimation, it's the same both directions, right? So if I'm going from solid to gas, well, that's going to be absorbing. If it's going from gas to solid, that's going to be releasing. The classic example of sublimation that you would know about is what's shown in the picture, dry ice, where I have solid carbon dioxide, same stuff you breathe out, solid carbon dioxide that goes straight from a solid to a gas as it goes through sublimation. All right. This is a graph of taking water as a solid, as ice, and then applying heat to it and measuring the temperature. And what's interesting here is that when it reaches 0 degrees Celsius, heat is still being added, it's still being heated up, but the temperature is remaining constant for this period of time before it becomes a liquid. And then when I have a liquid going to a gas, the same thing happens here, that for this period of time, heat is still being applied, it's still on the stove or whatever, but it's staying at 100 degrees Celsius until it completely changes into a gas. So where is the energy going? The heat is still going in. It's still getting heated up. What is happening with the energy that's going into the water? And the answer is the energy is changing the movement type of the particles. So when I have a solid, all those particles are vibrating, right? They're vibrating around. And then once it melts, that energy that's going into melting it is causing those particles to no longer be stuck in place, but now they can actually kind of break apart a little bit and start rotating around, moving from place to place. They're still vibrating, but they're gaining other types of movement, and they're able to move out of being stuck and vibrating. Okay, and then when I have a liquid going to a gas, this is those particles breaking apart, so now they're free to move all over the place and spread out as they are in a gas. So they no longer are closely packed, but they're able to break apart from the other particles and actually spread out through whatever container they're in. So when I go from a solid to a liquid and a liquid to a gas, that energy is going into separating the particles and having them start to move in different ways. So essentially, it's like breaking the bonds between the attractive forces between these particles so that they can move in a different way to change state. All right, well, that's it for today. That explains the particle theory of matter, hopefully, and how that actually fits into the different states that you know about from Science 7. Have a good rest of your day.